Good morning, everyone. Today is March 23rd, 2019, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. And we meet here every Saturday morning, 10 a.m. Eastern Standard Time or 7 a.m. Pacific at FuseMe 359-25732. So please support our mission at naturalphilosophy.org, where you can join us, or you can find us on Facebook, and you can also find us on YouTube. You can find previous recordings of this conference there. And we invite you to help us out by joining Basecamp at hq.naturalphilosophy.org, where we organize our activities. So rules of conduct is that we would like everyone to treat all the other participants politely. Please no insults. I think it's okay to tell people that they are incorrect, and more importantly, to explain why they are not correct. But please, no personal attacks. And we are having our conference coming up in June 26th to 29th, and that's coming right up. It's already March, so think about signing up. And we'll be having Dr. Gerald Pollack as our Special Lifetime Achievement Award. So today we have Bob Gray, who will be talking about Weber electrodynamics and mass increase. And we also have Alistair Riddoch, who will tell us something about his UUB theory. So Bob, why don't you go ahead and take it away?
Okay, need to share screen.
Yes, so let me promote you.
Yeah.
Nope, I de-promoted you. Okay, I promoted you again. Go ahead and share screen.
Okay. And let me make it bigger.
Yeah, go with slideshow presentation this. And yeah, move the little.
Yeah. Okay, so
out of there.
I'm always working on some form of Weber electrodynamics, thinking about that a lot. And
so why don't you explain to us what that means, Weber electrodynamics?
And perhaps I can simply say that's an alternative to Maxwell electrodynamics. I have done a presentation previously on Weber electrodynamics, and it's a lot of math. Not that it's difficult, it's just for this forum, there seems to be an awful lot of math. But anyway, I'll just say that it's an alternative to Maxwell electrodynamics. I actually consider it a correction to an expansion of Maxwell electrodynamics. But this week I was thinking about Weber electrodynamics and the special theory of relativity, and whether or not Weber electrodynamics has to significantly change in order to accommodate any results of the special theory of relativity, or if there's some other approach. I know J.P. Wesley has suggested an alternative energy potential for Weber electrodynamics, which is, he thought, more in line with or can give some results of special theory of relativity. It's the high-speed approximation. If the charged particles or charged bodies are approaching the speed of light, then the thought was Weber electrodynamics fails. And I'm not so sure that that's true now. And in particular, here I'm going to show Weber electrodynamics. If you go to the high speed, meaning approach the speed of light approximation, you do get a mass increase, the same as what we were taught in these special theory of relativity classes, but from Weber electrodynamics. So I know a lot of math here. This is just the notation that I'm using. Over on the left is a coordinate system. I have two charged bodies sub S meaning source, sub T meaning test, charge body, or detector. And then these are just positions, the relative position vector, the magnitude of the relative position vector, a unit vector in the direction from the source to the test, the time rate of change of the magnitude of the distance between the particles. Anyway, that's just the notation, just so you see what the math symbols mean a little bit. So you might say in Maxwell, or naively, force on a charged body, F is equal to Q times EC. EC is what I'm calling a Coulomb field. So the force on a test charged body due to a Coulomb field, and then using F equals MA, equate the two together. So you have QE is equal to MA. Okay.
So let me see if I can, so intuitively, you're saying that your source is just kind of fixed in space, and that's emitting the Coulomb field. And so you're measuring the force on your what do you call your test charge. So that's kind of free to move is what you're saying. But from a theoretical standpoint, it's like your test, I'm just trying to figure out what the difference between your test charge is and what your source is.
Right. So eventually, what I have in mind is a accelerator of some design, which is accelerating the test charge body, like an electron, accelerating an electron through a potential difference. What I'm saying a potential difference is this Coulomb field. So from here, you would expect then the force Q times E equal MA. But what is seen in the accelerators, apparently, is not MA, but gamma MA, where gamma is this factor over here from special theory of relativity. And some texts call this, or used to call it, a relativistic mass increase. I think they're tending to get away from that terminology and calling it more of relativistic momentum change. But for
this is a little bit
presentation,
different. So usually you say, I guess, force equals mass times acceleration, but you're saying that the specific force between charged objects also obeys this mass increase formula.
This is my understanding of what is seen in the accelerators from the special theory of relativity. It's not just MA, there's a gamma factor in front that's coming from the special theory of relativity.
Well, what's confusing me is that accelerators don't have test charges or Coulomb fields. An accelerator,
some do. For example,
they use more like magnetic containment.
That's containment, but a magnetic field cannot, or a force due to a magnetic field cannot accelerate the charged body in the direction of motion. And so to get that acceleration, there's an electrical potential in some accelerated designs, and that is what I'm calling the Coulomb field here. So anyway, in the Weber force on a charged body, if you look at Weber electrodynamics, can be written like this: the charge Q, and then what I call a Weber coupling coefficient, gamma sub W, and then the Coulomb field. And this gamma sub W, again, if you look at Weber electrodynamics, is given by this expression. So that would mean that the force Q gamma W E is equal to MA. And so what you would then expect to compare apples to apples, the expression QE would equal to 1 over gamma W MA.
But aren't those just constants against the MA?
Which constants?
Well, no matter how you cook this thing, anything in front of the MA eventually ends up being a constant, whether it's 1 over YW or
This one actually,
YMA, or
this actually depends on the velocities. This R dot is the speed of the magnitude of the distance between the source and the test charge.
okay, so
And
that
then the double
YW
dots are
isn't a
accelerations.
constant. That
That's not a
changes.
constant.
So
Neither
if you
is,
go,
let me go back to the one in special theory of relativity. You see this gamma of special relativity has this velocity squared. So as the velocities changes in special relativity, the gamma will also change, so it's not a constant. Anyway, back to
but that's
Weber.
so you're just showing the differences between special relativity formula and Weber's formula.
At the
And this
moment,
doesn't have
yes.
this doesn't have anything to do with Maxwell's electrodynamics, does it?
Well, Weber electrodynamics is an extension and correction of Maxwell electrodynamics. I'm not using, well, let me just go on here. So as the speed approaches of the test charge body approaches the speed of light, we can make the approximation that this speed squared over c squared is going to be much bigger than the acceleration over c squared. C squared is huge. So I'm going to make the approximation. We can discuss validity or not, but I'm going to drop from this coupling coefficient, this gamma w, the acceleration term. And so gamma w is approximately 1 plus speed squared over c squared 1/2. Then, as you know, everybody that loves math knows, we do an expansion of 1 minus something x to the 1/2 is equal to this expansion. And then I can say my x is equal to this speed squared over c squared, and I can get this expansion. And I can use that in the gamma w up that I show at the top. So gamma w now becomes 1 minus speed squared over c squared to the 1/2. And so now the force equation looks like this. The QE is approximately 1 over this expression, MA. Use the relation that R dot is equal to the dot product between the direction from the source to the test body and the direction of the velocity, relative velocity. That gives us this expression. And now I'm saying that, for example, in an accelerator, the source charges may be in the laboratory frame. I'm going to take the laboratory frame to be the stationary frame. So the velocity of the sources are going to be 0 in that frame of reference. So it's this V sub TS is really just V sub T, the velocity of the test charge. So I can put that into the expression. Then I can make a small angle approximation that the dot product is the magnitude of the unit vector, which is 1, the magnitude of the velocity of the test charge, which is just V sub t, and then the cosine of the angle between the unit vector and the velocity. Well, in an accelerator, the source charges are in front of or behind the test charge, so I can make a small angle approximation that the cosine is approximately equal to 1. And then I had this final result, QE is approximately equal to this 1 over square root of blah, 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 m times a. And that is the special relativity result, gamma ma. And so from Weber electrodynamics, using a few approximations, we actually do get a result from the special theory of relativity. I thought when I figured that out, I thought that was rather a big wow, because I had always thought that Weber electrodynamics had nothing to do with high velocities. You must always use a low speed approximation in Weber electrodynamics. But here is a high speed approaching the speed of light approximation, and we get a result from special theory of relativity, or more important, matching up with the experimental results where they have to use the special theory of relativity. And so anyway, those were just a few thoughts and discoveries that I made this week and that I'd share with you all.
So I can understand the approximation of when you approach the speed of light. I think that seems reasonable. But I don't understand this small, large angle approximation. I mean, I would imagine that a test charge approaching a source charge would approach at all angles. So I don't know what this cosine of theta plus or minus 1, I mean, what kind of approximation is that?
So I'm assuming that back here on this diagram, and thinking of a particle accelerator, that this source charge body here is generating an electric field which is accelerating this test charge. And it's acting along this vector, this line here. So the velocity of this would either be in, oh, come on, crap. Would be in this direction or in this direction. You see, or in this arrow direction.
Yeah, it would be tangential to the line between them.
So the cosine between this vector and this vector, or this vector and this vector, that cosine of the angle is going to be cosine of either 0 degrees or 180 degrees. And that's why the approximation, the cosine theta, is either going to be +1 or -1.
Well, but the problem is when you have a charge and accelerator, it's moving. So that angle would be constantly changing. Does that have any effect upon this approximation?
I don't think so.
Because I would think that, if you had...
As this gets closer and closer and closer and closer, and then there's maybe, when it's real close, there's some issues. But during the primary acceleration period, it's almost in line.
Well, I'm thinking that an accelerator would be accelerating your little point, your charge there, your QTI, from the left to the right. So if you drag your particle going from the left to the right...
Yeah, well, I don't care if it's like this. I mean, that's okay.
No, I mean, I'm talking about, because I'm just thinking that you're talking about accelerator. Your source charges are going to be fixed. Your test charges are going to be moving relative to that thing. So I'm still not quite sure. I mean, it's like obvious that between the line, at any straight line you can put between any 2 points, the cosine of theta is going to be 0. Well, of course, it's by definition almost. So why would you even bother putting that in? What's this? Does Weber dynamics demand that, or?
Yeah, that's any dot product between two vectors is equal to the magnitude of the two vectors and then the cosine between the two angles. So the cosine is coming because of the mathematical expression of a
there are no
vector
two
dot
angles.
product.
If you had 3 particles, then you'd have 2 angles. But between 2 points, there's never any angle.
Well,
right?
it's between.
Straight line doesn't have an angle.
It's between the two vectors. One
you
vector,
have to have 2 vectors. What are the 2 vectors here?
The 2 vectors are this vector here from the source to the test charge, and then this vector or this vector, the velocity of the test charge.
See, now the velocity is always,
and that's
so
this velocity.
That's your second arrow, and certainly the cosine of that thing is not going to be 0.
The cosine is going to be 1. The angle is going to be 0 or close to 0.
The cosine is not going to be 1 either, because that angle is going to vary quite significantly, right? That's the thing I don't get. So you're saying that the second vector in your picture, going back to your picture there,
right?
You need to draw in the second vector, which is the let's suppose the charge is translating from left to right. So you have
It
to
wouldn't
draw
be.
in that vector.
The acceleration of the test charge would be in the direction of the source or away from the source.
Yes, the
Because of the
acceleration would
electric.
be, but the actual vector direction of your particle. So just draw an arrow from your test charge to the right. So that would be directly to the right. So that would be like a 33-degree angle to the vector that's pointing to the test charge. See, now if you do
Why
that,
would I draw this arrow? Why would I
because you
draw
have,
this arrow?
because you're saying that there's a cosine. You're saying that there's two vectors. So that
Right, and
second vector is the second vector. Because you're talking about the velocity of the test charge, right?
Right, and that's excuse me, darn it.
I'm just trying to understand where the cosine is. Because there must be a cosine. If you have...
That's this vector. It's this vector here, copy, or it's this vector here. It's not this vector. And so it's the angle between this and this vector, or between this and this vector. This vector and this vector are approximately zero.
Well, I mean, it's not approximately zero. It's absolutely zero, because you're just saying that.
Well, no, in the accelerator, there's an annulus with a hole in it, which the particle goes through. So there's I'm not going to be able to draw it quickly, and I don't want to take the time. Okay.
But I'm not sure how that would...
Yeah. It's the function of the accelerator that the moving test charge body is approximately in the direction of the electric field that's causing the acceleration. And so that angle is going to be small, about 0 degrees, or it's going to be 180 degrees, depending on the orientation of the field. But anyway, to me, the point was that Weber electrodynamics in a high-speed situation can, under the appropriate approximations, give a result like special theory of relativity. And I just thought I'd share that. Don't need to belabor it, I guess. So let me see. Why don't
well, I mean, that's a good thing, because any theory that has coverage in that field should come up with what are the observed empirical results. So that's always a good thing.
Okay, thanks.
Could I just ask one question, Bob? I think the demonstration was interesting, but the origin of the gamma W term in the Weber electrodynamics in the first place, I mean, is that experimentally based? I thought it was basically postulated, or, a theoretical construct of the theory itself. What is its origin?
Right. The original development goes back to Ampere electrodynamics in the 1820s, 1820 to about 1826 is when Ampere did a lot of experimentation and came up with what we call Ampere's force equation. And then in about the 1840s through, I don't know what it was, 1860s or so, Weber took Ampere's force equation and wanted to develop some mathematics that such that he could derive Ampere's force equation from a potential. So if you take the derivative of the potential, you get a force equation, and Weber wanted to be able to derive Ampere's force equation from that. And so Weber started with Ampere's force equation and did a lot of math and eventually figured out a potential equation from which he could derive Ampere's force law. So Ampere's Weber took that potential, and you take the derivative of that with respect to the magnitude of the distance between the charged bodies, and you get Weber's electrodynamics force equation. And that is what I'm using. Weber's force equation comes from his potential energy equation, and from Weber's force equation, you can get Ampere's force equation, which is experimentally based on Ampere's work. So that's where that's coming from.
Okay, thank you. But in the last analysis, in order to discriminate between the predictions of Maxwellian electrodynamics and Weberian electrodynamics, you really need some very accurate experiments with various velocities, I suppose, of the test particles. That hasn't really been done. I mean, both seem to be consonant with Ampere's work and so on. Just different ways of progressing.
From what I've read, there are some papers, particularly from J.P. Wesley, who's pointed out some experimentation which is in favor of Weber's force equation rather than the Maxwell electrodynamics, particularly around the Z antenna. It's an antenna which is shaped in the letter Z or Z, and it's hung up, and it either rotates or it doesn't rotate depending on Weber electrodynamics or Maxwell electrodynamics. That experiment was done, and according to Wesley, it favored Weber's electrodynamics. There's also something called a Hering furnace, the exploding wire experiments, which utilizes Ampere's force law, but that wasn't Weber. And I think Professor Assis has suggested some experiments that would distinguish between Maxwell and Weber, and I don't remember the details of that at the moment. There are some suggestive experiments that favors Weber, but I can't say that it's absolutely definitive at this point. Now, if you want to talk mathematics, I can show you very easily where the mathematics of Maxwell fails. It's an inconsistent, mathematically inconsistent set of equations. It doesn't work. And then I can show you how to hatch it up a little bit by adding a little term here and there, and lo and behold, you actually get Weber electrodynamics completely by fixing up.
I think you may have given a little demonstration some weeks ago on that. I'm not sure if you are talking about something further than that. Do you recollect that?
Yes, I do, and I've refined that presentation significantly, and so I think it's much clearer how Maxwell electrodynamics is mathematically inconsistent, what it would take to make it mathematically consistent, and once you implement that, you end up with Weber electrodynamics.
Okay, thank you very much. I'll leave it up to Franklin to decide whether you should give that presentation now or at some other stage. Thank you.
I see, Bill, you've got a flag up. And then Harry?
We've got some things that are not too clear at the moment. One is when we talk about Maxwell, most of us are talking about not Maxwell's version of electrodynamics, but Oliver Heaviside's version. Maxwell was working in terms of matrices, and Heaviside was working in terms of vectors. And when Heaviside did that, he simplified Maxwell's work. Maxwell was based on Ampere's law, Faraday's law, Gauss's two electrostatic magnetostatic laws, and then Lenz's law and Lorentz's law. Well, what Oliver Heaviside did is he got rid of Lenz's law and Lorentz's law and threw away some of the terms in the remaining four laws. And so that's what we call Maxwell's equations. But if you solve all 6 of the empirical equations of electrodynamics simultaneously, which I do in my book, The Universal Force, what you find is that Lenz's law is the origin from the empirical laws of electrodynamics. Lenz's law is the origin of all relativity type things, special relativity. And so it turns out that special relativity is in agreement with the more complete version of Maxwell's electrodynamics, and it's in agreement with the work of Weber. By the way, the work of Weber is, I think, a few years older than Maxwell's work, and they were competing for attention among the scientific community. And you mentioned Asi, and I think Asi is one of the best known scientists who've been working with Weber's law, Weber's electrodynamics, and he's made a lot of progress in that.
Right, and you are correct. When I saying Maxwell's electrodynamics, I do mean the Heaviside-Gibbs vector electrodynamics that's taught in the textbooks that at least I was using, Griffiths and Jackson and all those guys.
Right. Now, the important thing to notice here is that in both Weber's electrodynamics and the more complete version of Maxwell's electrodynamics, the formulas that involve 1 over the square root of 1 minus v squared over c squared, or the gamma term, they come out of these two approaches, Weber's and Maxwell's, without any of the assumptions that is made by Einstein for special relativity. And I gave a talk before the American Physical Society once showing that these assumptions that Einstein makes are not true, and that on the basis of light, the Einstein's origin of relativity theory is false, because it's based on assumptions that are known to be false. And one of those assumptions is that the universe is homogeneous and the same in every direction. And that's not true. We know that the universe is not made that way. We know it has particular structures, and they occur over and over and over again. And there's centers, for instance, of our solar system that's denied by special relativity.
It's amazing. It's really amazing how, forgive me for saying it this way, how screwed up physics is these days. It's really amazing when you start looking at these things.
Yeah. Now, what they did in order to keep Einstein's theory of special relativity is they changed the scientific method to be the existential scientific method, which means, and if you have to study that to find out what all that it means, but what it means basically is no theories in science are falsified because they incorporate false assumptions. And this existential theory was again modified again in the 1960s to be the postmodern philosophy of science, which continues that same assumption, but also makes each of the fields of science a separate silo, so that chemistry is separate from physics, and biology is separate from physics, and all that sort of thing. And so that is the way we have developed. And the question is, why did we do that? And there's a lot of different answers. There's the religious answers, and there's other types of answers that say why it was done. But basically, all of the theories from about the 1820s and 30s to the present day are used to combat religious ideas. and that seems to be the reason why they took the role of logic out of science, so they could do that. Otherwise, they would be disproven. And
all right, so Harry's raised his flag. Go ahead, Harry.
My question, well, I didn't understand any of it, so my question would be, why didn't you start off with the axioms of Weber dynamics? And because your presentation doesn't really flow from the axioms, because you didn't present any axioms, but so I couldn't understand what you're talking about. The other thing is, I'm not really sure what you mean by Maxwell electrodynamics. I don't know that there is such a thing as Maxwell electrodynamics. All I know is that what people call electrodynamics is traditional electromagnetic theory, which basically Maxwell incorporated into his treatise and modified that over a period of time, and the main modification was Einstein's special theory of relativity. So it looks to me like all you're really talking about is the Einstein modification of electromagnetic theory, and I don't really see that has anything to do with Maxwell other than an historical connection.
Yeah, I would agree. As I mentioned earlier, when I speak Maxwell electrodynamics, I mean open up Griffiths or Jackson or any of your favorite electrodynamic textbooks. And
well, what do you consider the main equation of this so-called, quote, Maxwell electrodynamics, the Lorentz equation?
No, well, there's two answers. One is what is in the textbooks, or what do I think? What do I mean by
you, I mean, when you say electrodynamics, what do you mean? Do you mean?
I mean Maxwell's 4 equations in the textbooks in differential form, plus the fields written in terms of potentials, plus the potentials written in terms of the charge density and current density functions.
So how does that differ? How does any of that differ from Weber's theory? I don't think it does.
The difference is that Maxwell's electrodynamics, again, the 4 equations.
Well, I brought this up before. These equations, these 4 Maxwell's equations, aren't electrodynamics. Electrodynamics is the Lorentz force law. Okay, electrodynamics means the actions on charged particles, okay, like an accelerator. That's electrodynamic. What you're talking about here with 4 equations is electromagnetic theory, which is something different. So what we have, in my opinion, is a terminological difficulty. So I want to know what about these 4 Maxwell's equations? Is that what you're talking about? Or are you talking about the Lorentz force law on a moving charge?
When I say Maxwell's electrodynamics, I mean all of that. The force equation.
That's not Maxwell's electrodynamics to me. Okay, electrodynamics is forces on moving charges.
Right. So I'm looking at the force equation as in Jackson Griffiths, F equal Q times E plus QV cross B plus Maxwell's 4 equations plus the fields in terms of potentials plus the potentials in terms of the charges. All that together as a system, mathematical system of equations. That's what I mean by Maxwell's electrodynamics. And you're absolutely right. That's not the standard way to say it. It's not necessarily correct historically. But that's what I mean by that terminology.
We can do better than that. In his book, Mathematical Principles of Natural Philosophy, Isaac Newton defined the way to do electrodynamics. He says you perform experiments and you find the empirical laws. 6 empirical laws were found. then you try to solve these empirical laws simultaneously. And that's where the problem began, because scientists were not used to using vectors or matrices at that time. And so when Maxwell started using matrices to get the solution to the 6 empirical equations.
Excuse me, Bill. I think he used quaternions.
Quaternions, yes. But that's a matrix. It's a 4x4 matrix. And then people like Oliver Heaviside came along and threw away 2 of the 6.
All right. Now, here again, what Oliver Heaviside was doing was he was trying to solve wave equations on transmission lines. Okay. And it didn't really matter to him. And of course, he was also interested in the field of a moving charge, and was one of the early pioneers on what is the field of a moving charge. So he was really only dealing with a subset of problems of electromagnetic theory. So he didn't really need all of the equations for what he was doing, or at least he didn't think he did.
Become known as Maxwell's equations, the equations he worked with. And
he worked with those equations to solve what he was working on, which was primarily waves on transmission lines.
Right, but that is, in textbooks today, that is what they call Maxwell's electrodynamics. And
I agree that he adopted the Gibbs vector formalism because the quaternion formalism was too difficult.
Yeah, and but you can do it with vectors, but it's they didn't actually do that. As you say, he was only working on certain problems. In my book, The Universal Force, Volume 1, I actually take those 6 empirical equations and solve them simultaneously. And when you do that, you see that one of the force laws that he got rid of, which was Lenz's law, that one gives rise to what we call the relativistic effects in electrodynamics. And you can see that because they didn't use that law, Lenz's law, properly, they left out the relativistic type effects in electrodynamics. But of course, at that time, nobody was able to measure those relativistic effects. It was only after we started making accelerators and stuff like that that we got interested in it, and that's what caused the work of Einstein to be accepted. But if you, as I said before, if you look at his assumptions to give rise to it, see, he's applying relativity theory on top of electrodynamics. He doesn't admit that, oh, well, that comes directly from the empirical laws of electrodynamics. Einstein never admitted that, but that was the case. And some people knew that, I believe, and I published that and in the book. And then when I pointed out what was wrong with relativity theory, you can't take a false theory and add it to a theory that's based on experiment. And Einstein's work is based on assumptions, and those assumptions are known to be false. And so I think there are 5 of them, 5 assumptions that Einstein makes, all of which are known to be false. And so you can't do that. But the results he was getting when he applied it to electrodynamics come directly from the empirical laws. You don't even need relativity theory at all. And you don't have the false ideas that relativity theory incorporates in addition to those gamma, or the square root of 1 over b squared over c squared. Those things are
well, if what's being said here is correct, then all of modern physics is completely wrong and erroneous. Because as my understanding is that the so-called Maxwell electrodynamics, as Bob says it, is embedded in the Hamiltonian Lagrangian equations that are used in elementary particle physics and all of quantum mechanics. So that would say that's all wrong, because the Hamiltonian equations and the Lagrangians that they use are completely incorrect.
Yeah, that's what philosophers of science say, that the removal of the role of logic from science has caused all of the theories of modern science since about the middle of the 1800s to be false. They're approximately right, but they're false.
But you're referring to two separate things there. I mean, in one case, you're talking about the falsity of the assumptions and the absence of logic. On the other hand, you're talking about, Harry, I think a mechanism like a Lagrangian or a Hamiltonian formalism in terms of general coordinates and looking at total energy systems.
So that's based on Einstein's theory of relativity, which they use the four-vector formalism. They convert the Maxwell's equations through Einstein's relativity into this four-vector formalism, which gives the equations for the gradient and divergence of the fields in the four-vector formulation, which is, quote, Lorentz invariant. Okay, and so I would say that what Bob means by when he says Maxwell electrodynamics, that's kind of what he's talking about. Are you familiar with what I'm talking about, Ian?
Yes, I am, Harry, and I do take it that extension in the special theory of relativity is probably incorrect. But I mean, the basis is classical. I would say what they're using, these Lagrangian functions or Hamiltonian functions, are basically classical. They're Newtonian. There is one other slight complication, maybe a little pedantic, Harry, in that the use of dynamic as meaning motion, which is common, where more strictly speaking, it actually refers to force, and kinetic refers to motion. So if you take that definition, that dynamics is the science which deals with all forces, whether they're in motion or static, well then electrodynamics would include electrostatics, and it would be separated. Electrokinetics would be the specific part of electrodynamics which deals with charges in motion.
Yeah, well, I'm confused by the terminology. My view would be, for Bob, my view would be, Bob, how do you, Weber electrodynamics, in order to be successful, it would seem to me, would have to you would have to show that it could be more successful in the field of elementary particles, where they're bashing charged particles together in accelerators, and showing that these reactions that take place are more correctly or properly explained somehow than the current method that they're using, which is based on quantum electrodynamics and the quantum theory they use. And you're right, they've extended the Newtonian idea of mechanical equations for a particle, a mass. Okay, and then they've extended those equations by the four-vector formulation of Maxwell's equations, which really basically they're only really dealing with the momentum, and then there's the I forget exactly all the parts of the four-vector, but the four-vector formulation transforms the Maxwell's equations into the Lorentz invariance electrodynamics, which they say is based on Einstein's relativity. So therefore that makes it right, because Einstein's relativity is right. And then based on that, all of quantum mechanics and elementary particle physics is based on that method of formulation. So that's what I would say Maxwell electrodynamics is. It sounds like
I'm
a
working on it. Yeah, I'm working
Are you
on it.
familiar with this four-vector formalism that they use in quantum mechanics?
Yes. Yeah.
And it seems kind of hokey pokey, doesn't it?
Well, sure. It's a real headache.
It seems hokey pokey to me because the assumption is that the electron is this mass, point particle mass, and I don't know. It's just, and then out of that they get this, but this point particle mass doesn't radiate like it's supposed to. But in effect, basically, all it is they get equations for the vibrational frequencies of electrons in atoms. Okay, and so I'm thinking to myself, well, anything that can vibrate could be an electron.
That's pretty good. Yeah. Franklin, you want to see if Alistair is ready for his presentation?
We can, although I've been I don't know if you guys have been noticing, but I've just been browsing the web here while you guys are discussing topics. So you're looking at, in Wiki, the mathematical description of Weber's electrodynamics. And so, you can see the formula that Bob showed here, which is basically reduces to Coulomb's force for low velocities, basically. So I'm not terribly surprised that, you find this dependency due to this initial mathematical description here that has c squared on the bottom there. Although I'm not terribly convinced that that's true, considering how big c squared would be. But my question is, so it looks like Weber's electrodynamic is based on Coulomb's force law. I mean, is that it? I mean, I thought you've always said that things like magnetics is based on charges in Weber electrodynamics. So that's how that's solved. But I don't see any of that in this wiki page.
Well, a couple of things. Don't believe everything you read on the wiki pages, particularly on things, quote unquote, they don't like, which one is Weber electrodynamics. And yes, I've interpreted Weber electrodynamics in such a way that there is no such thing as a magnetic field. There's a magnetic induction function, but I don't consider magnetic fields from a Weber electrodynamics point of view to be real. But the Coulomb field is real. And that's just my interpretation of Weber electrodynamics.
All right. Are there any other questions for Bob about this topic before we go into Alistair? No? Okay. Well, then let's go on to Alistair Riddoch. So, Alistair, are you ready to present?
Yes.
All right. Well, why don't we go ahead with you? You've got an hour. Go ahead and share your desktop again. Okay, we can see that. And yeah, you can drag that box out of the way.
Okay. Can everybody hear me all right?
Yeah, we hear you okay, and we can see your presentation. I think that's an appropriate size for us to read it.
All right, great. If anything turns out being the wrong size or you want something expanded or whatever, just let me know. I'm going to blow through the first part pretty quick. It just basically says, we know there's a whole whack of theories. There's like at least 24 listed in Wikipedia. So certainly at the very smallest scale of existence, we don't know what the heck is going on. Everybody agree with that? This page here, can you guys see my mouse when I move it?
Yeah, we can see your mouse.
We don't know what's going on. You mean in terms of gravity?
In terms of the physical composition of existence itself.
Well, that's a kind of a philosophical problem.
Well, I'm going to try and introduce logic to it. That's the whole point of what I'm speaking to today, is a proposed solution to the very fabric of existence itself, the very smallest of the small. I call it Planck mechanics, a lower scale than quantum mechanics. So I just put this part at the beginning just to say we don't know what's going on at the very smallest scale. We've got all these theories like quantum foam and quantum strings and quantum loops, causal dynamical triangulations and holography and what have you, supersymmetry. You all know there's a whole bunch.
But I would say that it's important to recognize that mainstream would say, for example, that everything is made out of atoms. So I think
yes, that's fine, but we're way smaller, way smaller down the scale than atoms.
Smaller than what? So the smallest thing we know of is an electron.
Smaller than electrons, smaller than quarks, smaller than leptons and bosons. Oh, bosons are force connectors. Smaller than hadrons, way down small as you can get, Planck scale. All right. So the process was, I was thinking a lot about gravity and pressure and how gravity works, for reasons I won't go into at this moment. But I wasn't satisfied with the fact that there's 24 theories and we've got two best ones, the standard model of the atom, the standard model of cosmology, and they don't reconcile. That all sounded like a bunch of crap to me. So I started with an absolutely clean slate, and I looked for what could possibly fill, like totally fill existence and explain everything we experience and observe. So I tried different shapes that maybe were in this vibrating lattice. I tried tetrahedrons because of the mathematics of electrons and neutrons. They lead you to like the differences, the 1836 and that. There's a pretty good case for tetrahedrons, but they don't work out, and everything would be triangular. The Earth would be triangular, and everything would be triangular. So I went through all the different, platonic solids and all that, got to regular perfect spheres. But then you run into the problem of, are you going to have friction or not friction? And if you don't have friction, there's no way to transfer rotation from one to the next. And because if you have friction, they're going to bind when they're in a field like shown here. So I tried different patterns of rotation, maybe like wiggles, or maybe like, where each one beside it would follow the line of a tennis ball as it rotated. I tried a bunch of things. None of them were satisfying.
So why are they not satisfying?
They failed to be able to explain existence the way we experience and observe it.
Like what? So what was wrong with, you said you had close packed spheres and you had a picture of that. So yeah. What was wrong with just that picture? And you mentioned something about transferring rotation. What was that about?
If there's no friction, there's no way to transfer rotation from one to the next. If there is friction, they bind. There cannot be friction at the Planck scale.
My question is, what is the motivation behind them rotating? Why can't they just be like ping pong balls poured into a drum, right?
Yeah, that's a possibility, and they're all vibrating, and that is a possibility. But then how does that turn into galaxies and stars and suns and planets when they're all just vibrating like that? And if you were to hit one of those, which direction is the is it going to propagate? It's going to go, if you hit it perfectly like a perfect shot in billiards, it's going to go straight. If not, it's going to like spread like this. It just didn't fit what we experience and observe.
Well,
and
I'm trying to find out what you're trying to talk about there, because
I'm just ruling out options. Remember, I started with an empty universe, filled it with somethings. What could those somethings be? And I don't want to introduce charges or action at a distance or mediumless waves, nothing. I want to look for what could possibly fill existence and explain what we experience and observe.
So if we're just talking about the medium, then I don't know why your close packed spheres wouldn't at least satisfy the requirement of a medium that can transmit waves, right?
If somebody thinks that they might and wants to work on that model, but there was some guy who had that model going way back in the late 1800s, early 1900s, and they threw it out. It doesn't work. But if people want to explore that, they can go right ahead. I can tell you it doesn't work. Maybe I can't tell you satisfactorily why it doesn't work, but I can tell you it does not work. It just doesn't.
I'm also curious, Lynn, that you tried all the other different shapes.
Yes, I did.
Tetrahedrons and octahedrons and
because, like I say, I was exploring. So I didn't spend a whole lot of time throwing out cubes, throwing out tetrahedrons, because there are reasons, like when you expand up to larger scales, there are reasons why they don't work. How are you going to explain fingers out of tetrahedrons?
Well, if you had sufficiently small tetrahedrons, yeah, you could make any shape you want out of tetrahedrons.
Yes,
right?
Because that guy who built those like geodesic domes, Buckminster Fuller or something like that, he says you can make any shape out of tetrahedrons by just expanding one of the four edges. But just work with me here, because I came to the better answer, so I don't need those lesser answers. That's the whole point.
I'm trying to find out why they're lesser answers. They don't seem to be lesser to me.
Just let me flow, okay? Let me flow.
Right. Go ahead then.
All right. So then one day I was doing a lot of research into weather, and the atmosphere of Earth, it kind of fades off into nothingness, but there's that really dense part before it starts to fade quickly into nothingness. Within it, there are weather cells called Hadley, the middle ones by the equator, the Ferrel cells, and the polar cells. And they're these tubes that spin around the Earth, and they've got this pattern, although this is exaggerated. And I'm just telling you how I came to clue into the shape of what I did find, what I propose. So I had this shape in my head as being like the event horizon between existence and non-existence, because outside the atmosphere is close to vacuum, inside the atmosphere isn't. And there's downs and ups and downs and ups and downs and ups within this weather pattern that's persistent. So then it happened in the same day. I was reading Scientific American. Can you guys see my camera okay? So
we can see your screen.
It's the only issue of Scientific American that I've probably bought in 40 years. And on the front page it said a crisis in physics, because nobody can figure out what the hell's going on. And this story with the what's on my screen there was in the magazine as well as the crisis in physics. This story is about the cosmic microwave background. And it had this shape. And I thought to myself, wow, that's an interesting shape, because you can see how it's got like this average height layer down the middle, and then it's got these ridges, these ins and outs. And as the ridge goes around, it gets less and less flat and more pointy, and it's got a left and a right, and it's got an up and a down. I wondered, so I asked myself the question, what if these were super, super tiny and the universe was filled with these and nothing else? So that's not what this article is about. This article is saying, if you look at the universe, the big universe, the cosmic microwave background, this pattern is the pattern that all of the cosmic microwave background put together makes. And I took that huge and I said, well, what if it was super tiny? Can you guys see my hands when I'm moving? Like, I don't know how tiny my picture is because I can't see myself. So
I don't think your camera is on. Yeah, your camera is not on.
Oh my gosh. I'll fix that pronto. Oh, there it is. Hey, now I can see me. All right. Okay, so you guys were missing like with the tennis balls and everything then. All right.
Yeah, we can see you now.
Okay.
Little blurry.
So, Scientific American, A Crisis in Physics, front page. Article about the cosmic microwave background. That's important. Okay. So that was where the shape came from, but I took the shape and gave it a different purpose. I said, what if it was ultra tiny, Planck scale tiny, and totally filled existence? And that's the basic premise of what I suggest is a physical mechanical field that creates and hosts a field of motion, and it's that field of motion that everything is made from. So the basic premise is an infinite number of these solid, they're non-divisible, they're Planck scale, ultra tiny. They always existed. They're the building blocks of the universe. They're never created. They're never destroyed. So in a sense, they're time immune or timeless because they have no beginning, they have no end. Time means nothing to them. Only motion and patterns of motion come and go, and therefore have the element of time makes any difference to the patterns of motion, but not to the building blocks themselves. So this is just a picture of the way they would be arranged. It's called hexagonal close packing. So that's where you have one, and each one has 12 surrounding it. 6 in a hexagon around it, 3 above it, 3 below it. And then when you move one over, that one is equal. It's got the 12 around it as well. That's an important ratio, the 1 to 12 there. So the article from Scientific American was talking about the cosmic microwave background. And it said when you zoom in, there are magnetic oscillations. And the oscillations have 2 polarizations, 2 types of oscillations. And they're E mode and B mode oscillations. This is an E mode, and this is a B mode. And that's what the cosmic microwave background is composed of. When you look at it and you analyze it fluctuating over time, it's made from these 2 wave functions. When you take those 2 wave functions together, mathematically, it creates this shape. Everybody following that? You take one of these and one of these, you mush them together mathematically, and you get this shape.
How is that mushing done?
I don't know. That you'd have to ask a guy named Mark Kamienkowski. He's the guy that came up with the shape, not me, but he didn't consider it as a universal building block. He was saying, here's the shape of the whole universe. And
To
I'm
me,
saying,
that's like
what
adding apples and oranges. How can you do that?
Well, sure you can. I mean, every image is math, and it's an equation. So this is an equation, and this is an equation. You know, x plus y equals z, blah blah, and you can mush them together and make another equation. That's like just math. So that's the important.
Yeah, but you can do all kinds of nonsense with math is the problem. So,
Yes.
Can you go back to what I'm not sure what E mode and B mode mean. Can you go further back up?
I mean, if you were to add these two things together, I think you would get something which would kind of look similar, like some kind of balloon animal twisted thing. Not that.
These are the oscillations of the cosmic background. So according to this.
Exactly. That's where the source of my proposed universal building block came from, is from the merging of the two oscillations that make up the cosmic microwave background. Okay, so this is the E mode polarization pattern, and this is the B mode pattern. This is what a B mode wave function looks like, and this is what a E mode wave function looks like. This is not my math. If you look up, this is like well-established stuff. You look up CMB polarization, you'll find article after article, E mode, B mode, E mode, B mode, E and B mode. It's well-known stuff. This isn't me hypothesizing this. It's well-established by Keck, by Bicep, and another one I can't remember at this time.
Now your E mode and B mode picture looks more like the electron shell in atomic theory.
Yeah, that's what the E mode and the B mode is.
But I don't know that has anything to do with the CMBR.
It absolutely does. That's what all these stories are about. Is I'm getting an echo from somewhere.
Yeah, that might be the same problem that Bob had. Maybe can you turn your volume down a little bit? Or maybe I'll mute some people. Maybe that was Harry. I think we're okay now.
Yeah. So that's just to establish the credentials of the shape itself. The mathematics is not done by me. The mathematics is done by some genius dude who spent years and years and years coming up with that shape. So that's just the source of it. Back to the Word document. Okay, this shape is one of these and one of these put together mathematically. This talks about the pattern of arrangement. So you guys know about the different ways you can close pack spheres. There's, square where they're sitting on top of each other, and then there's hexagonal, like having a set of billiard balls in a triangle, and then adding another triangle on top and another on top. It makes this. That's what this talks about. And when you've got one surrounded by 12, the distance from center to center and center to center between the outside 12 are all equidistant if they're perfect regular spheres, and from the center of each one around the outside to the center of the middle one is also equidistant if they're perfect regular spheres. In the case of the universal building block, they're not perfect regular spheres, but from center to center, they're going to average out that same way. So that was basically the proposal was, is it possible that the universe is made out of an endless field of these universal building blocks? And so to ask myself that question, then it led to the question, okay, if the universe is filled at the Planck scale, super tiny, with universal building blocks and nothing else, would it explain reality as we experience and observe it? Well, we have the electron orbital shells, which happen to be mathematically compatible with the universal building block. And we have more complicated ones. These are the heavier elements, but all of them have these as the lowest common denominator. Then I looked for other evidences. I came across pilot wave theory by de Broglie and Bohm, Louis de Broglie and David Bohm. It's also known as Bohmian mechanics and pilot wave theory. And David Bohm wrote a book. This is the cover of his book. Now, if you were to take this, like you would take a balloon and blow it up with air, it would look a lot like that. See how this is this angle, all these angles, it's like, I don't know if you can see it or not, but I see it easily that if I was to take this and blow it up with air, this could be the result I would come up with. Does that make sense to everybody? You could all just nod your heads. I can't see you, but I'll just keep going. If there's objections, say, oh, I don't know how that could make that. But and
why would you blow it up with air instead of mathematically transform it? You mathematically transferred the A and B field and combined them, and now you're just simply blowing it up with air.
Well, blowing it up with air adds a dimension in every direction out from the center. It's like taking something that's flat and making it three-dimensional. But I'm just saying there's a relationship between David Bohm's group wave. That's what's on the cover of his book, is his group wave. He says, this is what the universe is made out of. I say, well, it would make more sense for the universe to be made out of something that actually has some shape to it and it's not just flat on a piece of paper. In the material of David Bohm's theory, you come across this pattern. These are like force exchange patterns or something like that. And you'll notice this looks like a B mode wave, and that looks like an E mode wave. So again, I'm just pointing out that there's reason to see a mathematical relationship between a universe made out of these and pilot wave theory, which was what I had in my picture up here. Is, oh, it went pretty far. I suggest that when you rotate all of these, the motion that they have to go through, because they're not perfect regular spheres, so when they rotate, they're going to be shoving each other left and right, and because the ridges on one side and the other are offset, they're also going to be forcing each other to go like up and down as they rotate. You have to be able to like kind of see that. I don't have the ability to make an animation to show you that, but just imagine if you had, oh, I can bring that up actually. See, because of the shape of them and the way that the ridges are going to overlap, when this one rotates and this one rotates, they're both going to be going like this and like that, like this and like that as they're rotating. And so that is what I suggest makes this the pilot wave field. That's an image of pilot wave from Bohmian mechanics. It's just showing that.
What happened to the vibrations we were talking about before?
Well, they went away and we introduced rotation instead. But I want to also, there won't be friction, so they are all rotating clockwise. There's no friction between them, So there's no, like, normal rotation, you would expect they both go opposite directions. But in the Planck field, I suggest everything is going clockwise.
I think if you start with vibration, it has to persist vibratory, and then you have to have a little empty space between them to have room for the vibrations to vibrate. And I don't know how you can transition directly to a spherical friction or anything like that. I mean, you've got to retain the vibrations at this level, at this elemental level that you're talking about.
Well, I suggest that all of them are rotating, and they're all rotating the same way. There is no counter rotation. There's only clockwise rotation.
Michael, if there's clockwise rotation, the rotation is in a plane, which means that all there's polarization to the entire thing, unless you're clockwise. So you have a universe that now has a difference in one direction than it has in the other direction. It's perpendicular. So you have a flat world.
Yeah. One of the other things, see, we know that there's quantum spin is the properties of spin without actual spin, but this is at a lower scale. This is at the Planck scale, and I suggest there's actual spin. And what I suggest is that they're all rotating. There's no counter rotation, but if one is rotating slightly faster and one is rotating slightly slower, then there would be a delta spin. So there would be virtual, instead of there being left and right, there's 3 million RPM minus 1 or 3 million RPM plus 1, where plus 1 is like a right-hand spin and minus 1 is like a left-hand spin, but it's really 3 million plus 1 and 3 million minus 1. 3 million is just like a made-up number. Right. But they're rotating really fast. The whole field is rotating really, really fast. And as it rotates, because they're pushing each other around, you think of it like two sheets of hexagonal graph paper overlaid over top of each other with the centers are offset. And then think of in the field, each one that's beside each other is always going like slightly up and down.
Okay, I still have a problem with the fact that you say it's rotating clockwise, because if you look at it from 180 degrees the other direction, it's counterclockwise.
Exactly, yes. I agree 100%.
So you still have a universe that has a planar characteristic to it, where there's a polarization throughout it. You have a north and a south pole to the entire universe.
Absolutely, and that's one of the things we observe, is that within our universe there is orientability and polarization. And if you look at the physical properties of a single universal building block, I'll bring one up and zoom it in real good, because that's the whole point, is that I suggest that all the physical properties of the universe are caused by the physical properties of an individual one, or the properties of the group motion, or the properties of the gaps that are in between the balls. So if you look at this, see the centers of the ridges on one side are different than the center, like they're at a different height. They're offset. And you can see that it's got a left side and a right side, a higher side and a lower side. And from the center, it's got in, which is represented by blue, and out, which is represented by red. So you can always tell, if I take this, I rotate it, you can tell I rotated it, right? And if it was rotating clockwise, but you look at it upside down, well, you can tell it's going counterclockwise now. That means that the physical properties of the universal building block give you chirality, which is a left hand and a right hand. It gives you orientability. You can tell when it's upside down and you can tell when it's upside up. It's got hemispheres. And when you can tell which direction it's spinning, that means it's also got polarization. And those are all important things because those are all properties and features of existence that we experience. Chirality is important. In a wave-only universe, how do you explain chirality, left-handed and right-handedness, if everything is just waves? But if there's a physical medium hosting the universe, then there's the explanation for chirality. I better speed up a little bit. So we got the CMB is the source of the shape. And so I propose that the universe doesn't have a start date, that it's infinite in size and infinite in age, and the cosmic microwave background is not evidence of a Big Bang, it's evidence of the interference pattern caused by the host Planck field. Pretty good, eh? Because the Big Bang, it don't make no sense. I told you I was going to try and introduce logic, right? I got rid of forces and everything, and I'm giving a possible reason why we would have the shapes that we have, these and these, and I related it to some theories. So remember the close packing. If you look at Bohr's wave patterns, it fits right into a cuboctahedron. That's the shape. That shape is called the cuboctahedron. That's when you have one surrounded by 12 and you take the lines from center to center of all 13 of them, makes a shape called the cuboctahedron. And that lines up perfectly with Bohr's standing waves. There's a guy named Nima Arkani Hamad. I don't know if you guys know him or not. He was in that movie Particle Fever, working at CERN. And he figured out that if you take a couple of hundred Feynman diagrams and mathematically you mush them all together, Franklin loves that, right? The mushing of the mathematics. He made this thing called amplituhedron. And when you look at the shape of it, it too seems to have a relation to a degree, to a cuboctahedron. It's just that you took this one side and folded it over. So now this, if you were to take this and put it over there, you'd have that pattern again. Think of it like, you know how they made the hypercube, four-dimensional space? You take a cube here and a cube here and you connect it with all the dotted lines. Think of this kind of like a hypercuboctahedron, except instead of it going, you know, from here to here and connecting all the lines, think of it like kind of folding because of the motion. Just a suggestion. So you can see, hey, if I'm just showing some of the theories that are out there and showing how some of the patterns seem simpatico with the matrix, the field, and the shape of the universal building blocks. Also, there's E8 theory. Notice how it is also cuboctahedral in shape. And if we look at nature itself, we find lots and lots of examples of hexagons. We find like snowflakes are cuboctahedral in nature. Everybody thinks they're just six-sided, but it's more than that. The cuboctahedron is a much, much better match for the shape of snowflakes, the angles, in lots of ways. I'm just showing some some places where hexagons exist, and the North Pole of Saturn's a little special of a planet because its rotational pole and its magnetic field are lined up, whereas Earth has a rotational pole and then the magnetic field's over here somewhere. But Saturn, they're both aligned, and on the North Pole of Saturn, we have an inexplicable hexagon that's always there, a persistent pattern. This is some math they did in a computer to try and explain why Saturn has a hexagonal storm. Also, we saw the relationship between these. If you look at Jupiter and you look at it in the infrared, it has this shape pattern to it. And that's just, yeah, that's not very concrete. I'm just saying, if you had a universe made out of only these, would the things we observe in nature make sense? And I'm saying, well, this would, that would. Oh yeah, the Milky Way, it has huge gas clouds above it and below it that you only see if you look at it in the gamma spectrum and the X-ray spectrum. And if you look at it as a whole, it's an E-mode wave function. So again, if the universe was made out of universal building blocks, which have at their root an E-mode and a B-mode wave function, would it make sense that the Milky Way is the shape of a E-mode wave function, just like a hydrogen atom? Sure it would. Would it make sense that the Oort cloud also has that same patterning to it? Sure it would, because they're emergent. This is a talk by Neil Turok. He's the director of the Perimeter Institute, and he talks about a wave-only universe and why that cannot exist. It takes about 6 minutes, so I'm going to play it.
Well, I don't think we have time for a 6-minute video of the whole thing.
Yeah, we're at 11:40, so we got 20 minutes yet.
Well, more like 15 minutes, since I've got to go a little bit earlier.
Oh, dear. Okay, well, it's good you told me that now. I'll fast forward it a bit.
Yeah, fast forward to get to the good bits. What's his main point there?
Well, I'll tell you, I'll give you the quick and dirty. In it, he says, if the universe was waves, waves, and nothing but waves, then an infinite number of waves can coexist in a single point, in which case all the heat energy of a hot spot could dissipate instantly, simultaneously, and the sun would freeze. So existence cannot be only waves. That's what he's saying. And he says we know this. His conclusion,
nature gives us these clues. It tells us the answer. We just have to be smart enough to listen. Well,
darn it, I must have missed the punchline there. His conclusion was, he says, it seems to us as though the universe is all waves, nothing but waves, but we know it cannot be. He said, luckily, light is a particle. I don't agree with that. But if we look at the shape of a universal building block, right? Now imagine if you were looking at it from the top down. And now look at one of the proposed shapes of a photon. Looks like the UBB from the top down. So these were just images I tossed in because they help me explain things. It's really important that you guys understand, I don't suggest that objects are made out of universal building blocks. Instead, I suggest that they propagate through them. So this shows a hydrogen atom propagating through the Planck field, not made out of it. It doesn't carry them along with it. That model doesn't work where you carry the building blocks with you. Flowing through does work. It makes sense. So these pictures here were to show the difference. One is, okay, you know, you shoot the cue ball and it bounces around the table. Well, what if your table was full and you hit here with a cue? I don't know how many people here play pool. I've played a lot. And if this was full of balls and you were to hit here, the ball wouldn't move, but the force would go. Just as though the table was full. I mean, was just as though the ball went, but the ball didn't go. Only the information moved. Same in a Newton's cradle. So I don't suggest that we're made out of universal building blocks. When you see like two swinging back and forth, what's going through the middle one is the number 2. Or if there's 3 swinging back and forth, what's going through the middle one? The number 3. That's what we're made out of, the 2s and the 3s going through the medium is the suggestion.
Let's slow down here. Let's look at your pool table again.
Sure thing.
So the only reason the pool ball follows the direction you have is because the building material is already arranged in a pattern that's equal, that's right along the path of motion of
Yeah, because
pool ball. So what happens if it's not?
Well, if I was to hit this one here, then the force would go this way and this way at the same time. And so one of the half the force would go like this and come around like this. The other half would go up here, and come back down like that. I've played like a bajillion hours of pool in my life.
Right, but you never played a bazillion hour of pool with a table that's full of balls, because the force will not transmit the same as if it was an empty table like it is on the left. On the left, Correct. You can determine any angle you want.
Absolutely.
And get any results you want. On the right, you're not going to get that. You're going to get a scattering. You're going to get an entire inaccurate aiming. So to propose that space is full of little balls is going to mean that you're not going to get any straight line motion in it, except for unless the straight line happens to be in the exact alignment of the balls themselves already arranged.
Right. This is only here not to show you what is happening. It's to show you to flip your conceptual thinking. Don't think of us as being made of stuff moving around. Think of us as moving through. That's why this is here.
But if we move through, we have to follow the arrangement of what we're moving through. And the arrangement is geometric there. And so The only way you can get it otherwise is it's got to be totally random. It's the same situation with your direction of spin. Your direction of spin is clockwise, but if every direction of spin is clockwise, the entire plane, the entire universe is spinning clockwise. If I'm standing on top of the Earth and it's spinning clockwise, if I turn around and I'm standing on the bottom of the Earth, I get a totally different characteristic. I'm spinning clockwise, yet every experiment I do doesn't show me that I'm standing in a different orientation to the universe.
Correct. Now, remember that the proposal...
So the sterility doesn't work. The sterility only works in one plane for the entire universe. If you're standing upside down, you know you're standing upside down. The reality is we don't.
I understand. Now, remember that we're not made out of the balls. We're flowing through the balls. And remember that the balls are all spinning incredibly fast, millions of RPMs. And remember that they're all going one direction, but if one is going slightly slower, then it's going this way. It's like got a virtual left-hand spin, but it's not really spinning left. It's a virtual left because it's 3 million minus 1. And 3 million plus 1 is a virtual right-hand spin. So left and right-hand spin aren't actually left and right hand. They're 3 million plus 1 or 3 million minus 1. And what this is made out of is some plus 1, plus 1, plus 1, plus 1, plus 1, minus 1, minus 1, minus 1, minus 1, minus 1. But they gravitate towards each other because there's conservation of energy, and that's a natural property of the universe. So wherever there's going to be a plus 1, it's going to have a counterbalance. And that's going to create every point. Think of every one of these as kind of
we got about 5 minutes, so I want to make sure you get you through your presentation.
Well, is it really important to finish the presentation if the building blocks upon which the presentation is being presented is not foundationally argumentative? Because all we're doing is building error upon error then. So I think it's kind of important we discuss the building blocks and discuss the process as we go. Getting to the end, maybe we'll have to, in order to do that, we'd have to go through the presentation a second time and analyze it, if that's the way you want to do it, is go through the entire presentation, and then you would have to go through the presentation again to discuss the difficulties with it.
Well, since I think we're short on time here, would it be possible for Alistair for you to come back next week? And
sure.
And we'll go through those questions. Right now, I don't think we have time for questions.
All right.
Just want to make sure that you get through the main points of your presentation. We can think about it, and then next week we can come back with our questions.
Okay, dealio. If anybody wants to email me any questions or objections or ideas of where it might fit into what their thinking is, and here's how it might fit in, and anything you want to send me email, I'll try and respond or answer questions. I might not know enough to be able to answer every question. In fact, I know I don't, but I could certainly try.
Yeah, I think that would be a good suggestion. If anyone wants to do that, I'll put Alistair's email in the chat. And then go ahead and finish things off, and then we'll have to close the conference out soon.
Okay. So my thinking is, and I have is that each as it spins, it has to be cooperating with its neighbor. So it has its own momentum, but it also has the imposed motion of its neighbors. It's also imposing on its neighbors. And so between them, there's like cooperation. Think of it like a bunch of people in a barn square dancing, and they're all cooperating. And so because of that, they're jiggling up and down, they're shiggling left and right, they're moving forward and backwards. And so the pattern between them as they're all handing off creates this kind of vortexical motion where the center of this ball is going to be moving by about, the size of the ridge, left and right. So it's going to be going like this and up and down and forward and backward. And so that whole motion put together, the imposition plus its own internal momentum, creates this kind of balance where each one of them has I don't know how best to explain it. You guys, I'm going to get stuck too much into a discussion that doesn't fit in the time frame we have left. But the whole point is that each one has its own momentum, and it's getting imposed, but they're cooperating. And so where there's an imbalance, there has to be a counterbalance. And the imbalance and the counterbalance are going to orbit through the material. So it's not that these are orbiting, but the counterbalance and the imbalance are going to orbit through the material. And that's what creates these structures of orbiting, the orbital functions. I'll just show one last thing. Kind of like this. This is just mathematical. So if you imagine this whole GIF was full of universal building blocks, but imagine this pattern of motion going through it. And it's made out of imbalances and counterbalances. And so instead of charges being these magical things. Instead, they're imbalance and counterbalance. That's what I suggest. And then we can pick up from here and continue next week. That's all I need to say for today, since we ran out of time.
All right. Well, then, thank you very much, Alistair. And I have put your email, which is alistair.riddoch@gmail.com, in the chat. So if people want to start sending him questions, we'll do that. Maybe I'll just start up one of our standard email chains and attach this video to it and let people start commenting and see whether people have some questions there. So, but that will conclude this episode of the Science Chat. We had Bob Gray speaking first, and he showed us how to use Weber electrodynamics to derive the mass increase formula of special relativity. And so we discussed a little bit about what Weber was about. And then we had another presentation by Alistair Riddoch about what he's calling the UUB theory, where he is basing the world on his special form, which is related to the CMBR. And next week, since we didn't have time for questions, I think we'll start off with that next week. So thanks for everyone's participation, and hope to see you next week.
Thank you, Franklin.